I'm so honored, so excited to introduce this first speaker ever. Please join me in welcoming the first speaker ever to the City Code stage, warmly, Corey Haines.
Wow. Awesome. Okay. They actually just swapped my mic about 5 seconds ago, so good. Well, thanks, Garrett. That was something I would love to hear more often. Cool. So I figured a good way to start the day, of course, is to watch somebody code. A good way to wake up. We're all programmers. Also to see my old cat, Zach. Okay. That being said, I did a little font check, so it appears that everybody can see what I did. So the thing that I've been kind of liking lately is this idea of really getting in and understanding the lambda calculus. And a lot of people have heard of the lambda calculus, and they've heard of lambdas, and you always kind of read it, and it's kind of dry and hard to understand, and people explain it in terms of like cryptic signs and things like that. But so what I thought is, I'm a big TDD person, so I thought, well, what if you actually tried to TDD building up stuff with, we'll say the lambda calculus, but that's probably the last time I'm going to say it, and just talk about lambdas and using sort of the base principles of computation and the base principles of programming. So to start us off, we're going to actually build up sort of the basic structure. But as you can see, I have a pretty empty editor. So let's start by talking about what a lambda is. So a lambda, I'm going to use Ruby because Haskell would be too easy. And so in Ruby, a lambda is built with a little stabby pointer, because you're angry, and you get one parameter, and you get whatever you want to return. So in this case, this takes a parameter and then returns you that parameter. This is actually the identity function. The way you can execute it is you can do it in a way that kind of looks like it's calling a function, what we're normally with parentheses. You can always do it, also execute it like this, and this is what we're going to be using, which is more of a, looks like an array indexer, but it's actually execution. So if I run this, and everything is going to be down at the bottom when I run, because I'm in Vim, and why not have a mapping? So as you can see, it's hello and goodbye. It works. Of course, identity is a really kind of painful thing to write, so we're just going to call it I instead. And this, of course, still works. Hello and goodbye. Of course, having just one parameter is not always that great. Sometimes you need more than one. So if you do want to have what's equivalent to a multi-parameter or a two-parameter function, you basically have a one-parameter function that returns another one-parameter function. So in our case, look at this. This is a function. I'll stop using the word lambda. It's a function that takes a value, returns a function that takes another value, and then returns that first value. This is kind of weird, and it's kind of the constant. So if I execute it, it takes two parameters. So if I say hello world, I can also go goodbye. And no matter what I pass in that second value, I actually still get that first value back. So this is kind of a constant function. And just as with the identity, I don't like to type, so I'm just going to call that K. This is really hard to read, so you'll also see a little bit like this. If there's kind of a two-parameter function, we'll write it this way. And if it's very simple, we'll actually put it on one line. And then the last little bit of syntax is this Y is never used. So we're going to replace, whenever we have a parameter that we don't actually care about, we're going to use an underscore. It's sort of an idiomatic way of saying, I don't really care about this. Cool. So that's how lambdas work in Ruby. Very simple, but that's not really what we're interested in. What we're interested in is building up lists. And how do we build up lists? And how do you do that with just these, just lambdas, basically? So let's take a second and do it. Well, a good place to start, as I learned many years ago, I believe in the Sound of Music, the good place to start is at the beginning. So we're going to start with empty list. Now, empty list doesn't mean much if I can't actually detect that it's empty. So I want a function that can tell me whether it's empty or not. But if I run this, that doesn't do anything. It helps if I can output something. So I like to build things up with tests, so I'm going to build a function called assert. Now, what I expect to happen if I run this is I would really like it to print me a t, because the empty list is empty. So if I run this, that's our goal, is let's get this thing to print me a t. Well, uninitialized constant assert. Let me actually build an assert. I don't know what it does. I know it takes a parameter, right? I don't know what that parameter is, but let's just do a puts t. Oh, well, is empty I don't have. So I don't know what this is, and it doesn't really matter. So as I want to do, I'm just going to use the identity function. The identity function is kind of our no-op. It's kind of a thing that doesn't do anything. So if I ran this, of course, as we can do, you know, the whole test-driven development craze of doing just the simplest thing possible. And there. So, you know, I kind of live in a simple world. So I could say that I'm just done. Like, if all you have is the empty list, the world encoding is very simple. But of course, we don't just live with the empty list. So let's think about a list that is non-empty. So let's make a list that has, you know, one element. Well, how would I construct that? Well, I'd really like to be able to have a function called add to list. And I don't have anything to add to it, so let's just add the identity. So this is creating a list that starts with I and then ends with the empty list. And if I assert on that, well, I'd kind of like this to be F, right? Because that's not true. And that tells me a little bit more about my assert function. But if I run this, uninitialized constant add to list, well, that's no fun. So let's make that an I. Well, add to list takes two parameters, right? So let's build ourselves. We know how to build a function that takes two parameters. And let's just return identity. So here's a problem. I expect this to be F, but it's T. Well, if I take a step back, I realize that that's because I kind of was a little too simple. Now, whenever I'm doing any sort of test-first or test-driven sort of building up of a system, you know, starting with these simple things, and then once I get a little bit of differentiation, that's when I come up and I say, okay, what is different? Well, I want assert actually to be puts T or puts F, depending on this value that comes in. So let's do that. Let's move this. Let me write a little thing here. Assert outputs a T if given something that's correct, and it outputs an F if given something that's wrong. Well, that's nice. The term we use for that is, of course, a boolean. Now, what I run into is that I kind of have a problem here in that correct doesn't make sense. So let's use this term true and false. So I need to build up assert. Let's actually do a little bit of playing here with assert. So what I need is assert to give me a T if it's true. So let's build this. I expect this to be a T. This I expect to be a F. If I run this, my favorite, uninitialized constant true. I don't know what these are, but let's run them. Okay, so what I run into is, well, true, I want it to actually puts a T, right? That's what my definition says, is that T needs to give a true. And since it's a function, I should be able to just call it here, right? And in this case, I get my T. I guess I can see it on my screen, too. But I don't get the F. So let's come back here and build up our F. Huzzah. So I get what I want, T and F. That's pretty nice. So if I come back down here and do this, I don't have anything because, well, now I know that assert takes a boolean. So is empty is a function that what does it have to return? It has to return true, because it's a Boolean that it's returning. And there's my t. Now the problem, of course, is that it's always going to return t, but I need this one to return f. I need is empty to return a true or a false based on what is passed in. So as we did before, whenever you have differentiation, when you have a choice to be made, take that choice and push it out a little bit farther towards the boundaries. So in this case, let's make empty list true, and then just return list. And if I run this, it helps if I actually define things before I use them. I get my t. Now if I run this second parameter, I get the t. I don't get an f because add to list needs to return false. So I have this now. So what I have is I have a way of defining whether or not something is an empty list or not an empty list, which is great. Now I'm done. But of course, with a list, there are parts to it and things like that. And when I'm doing testing, you don't want a mix of like t's and f's, because f's are generally considered failures. So instead, I'd really like to have a function that returns me, a true in the case of false. And this is usually called refute. So let's build refute real quick. So refute, what does refute look like? Well, refute basically is like assert except opposite. It's sort of flipped. It outputs an f on true and a t on false. So this should be f. This should be t. It's kind of the opposite of assert. And since I'm here and I'm going to be working with it, I don't have a refute. Now, what does refute look like? Well, it's kind of the opposite of assert. So I can't really do the same as assert, because I get a tf, tf, which is not what I want. I actually want it to be f and t. So we got a little bit of a problem here. Let me come down and comment these out so that they don't mess things up. Now, I've got two things that are effectively the same. The differences between them is whether or not it's a t or an f that is being spit out. So just like before, when I have things that are different, I want to pull that difference and get it sort of out towards the boundaries but close to the part that actually differs. It used to be that true and false were what differed in whether it printed a t or an f. Now the difference is what assert prints versus what refute prints. So let's come up here and let's bring our test back for assert so we can see. This I expect to be a t. This I expect to be an f. So my output should be tfft, but it's tftf. And that's because refute is not working. So let's take a moment and I'm going to comment this out. And I want to bring the differentiation back into assert. So what I'd really like to be able to do here is say, in one case, I want to put a t. In the other case, I want to put an f. And then I can just do it in the opposite direction here. So let's bring this into here. So what I'd like to do is actually take true and false. It would be really great if I could have them choose which one to do. So I'd love to be able to say, hey, I know Booleans are function, everything's a function. Let me pass you the function I want you to call in the case of it being true. That didn't work. And then let me pass you the thing I want you to do in the case of false. And then whatever you give me back, I'm going to call. And so that tells me I need two things that choose. One that chooses the first item, one that chooses the second parameter. So let's take a look here real quick. I don't know what these do yet. Well, I do. I just said. It takes two parameters and it returns this first one. False takes 2 parameters and returns the second one. So I've been able to sort of pull the specificity, what gets put, is that a word, into the assert, where the difference is. And so now I have TF. And if I can take this and bring it into here and just swap it, then I should have TFFT. And so I've built up myself. Now, if I look here, the second one is not used. So remember, sort of with we're sort of marking that those parameters aren't used by using an underscore. So we're still passing, but there's a little bit of, before we get back to lists, there's a little bit of duplication here. If you look, this pattern is duplicate. Duplication is all about sort of patterns and knowledge, not as much about the individual lines of code, but about the patterns. And this idea of passing the Boolean and then executing what comes back is something that's duplicate. So let's create a function that does that for us. One that takes a Boolean, something that it should do if the Boolean's true, and something it should do if it's false. And I'm just going to make up, because when you're doing this sort of work, you can make up whatever you want. And I'll just make up a word if, because that's I don't know. It's not used yet. I don't think anybody uses that for anything. So now I have if. And what if does is basically it does what I had here. It takes a Boolean. It takes what to do in the case of true, and it does what to do in the case of false. Well, what does it do? Oh, well, I already had that code in there. Let the Boolean choose, and now I'm back to TFFT. So I still have my asserts passing. And that puts us into where the only difference here, the only difference in this code, in assert and refute, is what gets sent. Now, I don't like to leave things dirty, so this is really the opposite. Refute is really the opposite of, or the inverse of assert, kind of. So it just seems like I should be able to do something like this and just use assert in my refute. So let's build that. I'm going to actually bring this. If I'm working on not, and I change these, rather than change them, let's do this. So, I had a friend who did plumbing, and he said the difference between plumbing and electricity and electrical work, they're exactly the same, but if you make a mistake in plumbing, it's often funny. And that's how I feel in Vim, is if you make a mistake, like just everything starts going crazy. So these, let's get back to serious stuff. So it just makes the opposite of them. So let's build not here. What does not look like? Well, not is pretty simple. Takes a Boolean. What happens? Well, if my Boolean is true, what do I want to have happen in the true case? Well, I want to return false. And in the false case, I want to return true. Seems like that should pass. So I have TFFT, FTTF, which memory serves, looks like what I want. So now I have a not, which means I can come in here and just say assert not Boolean. That cleans that up a little bit, and oops, you all know what my mapping is now. TFFT, FTTF. So that's pretty sweet. I've got everything working. I've got an effective if statement, an assert statement. I've got a testing framework, basically. Back in the day, this is all we had. We had to write our own assert methods, and it was being deleted every 30 seconds, too, and snow in the grounds, and all sorts of awful things back in the day. So there's one little thing, though, that I want to show that is really what I think is like the super cool part of this. So look at this. What is true? True takes 2 parameters and returns you the first parameter always. We've seen that before. In fact, we've seen it right here, the constant function. So true is actually this constant function, one of those very, very basic things that we talked about. Now, if true is the constant function, then false must be something similar. Like, it must be related to it, because false is kind of just sort of the other part of true. So what is it? It takes two parameters, but it returns the second one. Well, let's come up here and see what we have. We have k and I. So what happens? All we have is k and I. So what happens if I give I to k? Well, let's look. So if I have this thing, and I give it I, so I make, x equals I, then what I end up with is a function that returns the identity. So that means that no matter what I give this, I get the identity back. So let's see what happens if I give it goodbye or hello world. So if I take this, and it's a two-parameter function, takes one and returns the identity function. So if I do a puts on this, let me exit here so I don't kill everything. I get world, I get the second one. So here, if I use k of I, this is a two-parameter function that always returns me the second. So false is actually k of I. TFFT, everything works. This blew my mind the first time I saw it, because it's these very basic little building blocks, and you now have booleans based on an identity function and effectively a constant function. So everything's still passing. Oh, there's squeaks. Okay. Okay, so back to lambdas. So if I come down here, I believe these should still be passing. So everything's good. I've gotten assert, I've got refute. Everything's great. So that's nice, but I can tell if something's empty or not. But if you have a list, it's really nice if you can pull things out of the list. So since I have true, let me change this to actually be called a list with a true in it, and instead of the identity. Make sure these are still passing. So it would be cool. I know that the second part of this, I have an element list, but the thing that's left after it is the empty list. So I should be able to say, let me grab everything after the first element. So the thing that I added to. And we're going to just call that tail. That's what it's called. I'm not going to make up a word like if. So here I have uninitialized constant tail. Well, that's kind of weird. So if I have a tail, what is it actually return? I know it takes a parameter. Well, I guess I could just return the empty list. Ha-ha! So, of course, now I'm good. But if I make a list and try to throw myself off, there's a throw myself off by creating a list that is true, and then the tail of it is the list that is true, whose tail is empty list. In this case, the tail should not be the empty list. I should get a T. Like everything, I should get T's. So I'm going to just get rid of these because we're now testing. So I get an F. Sadly, I get an F. Well, it makes sense because I just actually wrote empty list here. So what I really want to be able to do here, and this is where we're going to walk into a little bit of what I like to call programming by wishful thinking, which is, I used to call it turtles all the way down, and then I watched the SICP videos from MIT and realized that they had come up with this concept back in the 80s and had named it, so I don't get to rename it. And, of course, they know a lot more than I do, so I'm going to use it. It's called programming by wishful thinking. And basically, what it is, this is, for me, a core part of doing testing and a core part of building stuff, is write the code you wish you had, and then get it working. You know, that's kind of all programming is. So what would be nice, empty list, I have it whether or not it's empty or not. But what I don't have is to. So it'd be great if my add to list somehow kept track of it. So it marked it that it wasn't the empty list, and then kept track of the list. So if I did it twice, I would mark it, and then I would have the original list. And that would be great, but I'm actually just building lists, so I don't have a way with this tuple having anything. But that's never stopped me before, so let's pretend we have it. So I'm going to mark the empty list as a pair. It's basically a tuple that has true and false. Is empty, in this case, just has to grab the first item, which will say whether it's there or not. And then add to list is going to capture the list and create a pair false in the list. And in this case, our tail grabs the second item in the list. So this is basically it works if I had a pair. So as with everything, let's take a step back and build pair. So what do I know about pair? Well, I can write a couple tests around it. If I create a pair that is true and false, and then I create a pair that's false and true, I can write some tests. So I can assert on the first item of true, and I can refute the second. And if I change this to false true, then I can assert the second item and refute the first item. Because this is the first true, the second is false, the second is true, the first is false. So if I run this, of course, I get my first failure. I'm still working sort of I wish I had. So let me look at what this is. So pair takes the first and this takes a pair. I don't know what it returns yet. Second takes a pair. And there's a kind of a core thing here where what we want to do is we want to look at these functions and see how they behave together. I don't know how pair works. I don't know how second works. But instead, their behaviors are defined by how they interact. Sort of the way the whole world works. Like I interact with a chair by sitting on it, and that makes it a chair. Otherwise, it could be a table or something like that. So the way I like to look at it is say, okay, well, pair takes a first and a second. First takes a pair. Well, what do I know about this variable? Well, I know it's a function, so I could call it. Right? Well, and I know that when I call it, I expect to get this item. And when I call this one, I expect to get this item. And since pair is a function, I know that I have to return a function here. What comes in? Well, it would be great if I just passed it, both of them, and then let first and second define which one to bring back. I'm going to call this selector. So the function, so first has to give pair a function that returns the first item. We've seen that. We have a function that always returns the first item. That's k. Second, well, we did this with true and false. We know how to give ourselves a function that takes two parameters and always returns the second one. That's k of I. Remember, we had it up here. So now, if we run our tests, everything's passing. So what we've just done is we've just sort of backed our way into pairs. And that's super fun. So let's clean this up a little bit, just because we don't have a lot of room. So now, if everything is good and this worked, then I should have my 4 t's here. Oh, it also helps if I don't uncomment the things that are commented. So there's my T. So now I backed my way into building pairs so that I could keep track of the lists. Now, we have tails. The other part of lists is, of course, head. You want to be able to take a list and ask it, what is your first item? What's the first item in your list? So if I do that, I should just be able to say, if I call, oops, not on there, if I just have the list of true, then I should be able to ask for its head and get true back. The same for list of true, true. That's not as interesting, so let's build one that is list of false and true. It adds false to my list true. And at this point, I can refute the head of list false and true. But I can assert the head of the tail of false true. Crazy. So if these tests pass, then I've got a working function called head that brings back the first item of a list. And of course, I don't have a function called head. And I have the same problem here. It takes a list, but what does it do? I don't anywhere keep track of what the element was. Now, there's a marker here that's telling me I'm forgetting something. And that's the fact that I have a core function here that has an underscore, which means I'm not using this anywhere. And so when you're building something up, you can, if you keep track by using these little syntax helpers that say, clearly this is important because it's here, but I'm not using it. So what I really want to do is a way to keep track of this element and return that element. So, well, I have pair already, so why don't I put my marker and then have a pair, which is the element and the list. And in this case, I actually want to grab the second of the second. So I have a pair, I need to grab the second one, I need to grab the second one of that to get my list. And let's see if we've broken anything with tail. Nope, we're still all passing. So now I have the element itself. And so I could build head by taking the first item of the second item of the list. And at that point, I'm all passing. And so what I now have is I have a working list implementation based entirely on just these small little lambdas. And you can build all sorts of crazy things with it. You can get into numbers equal, which is an exercise I will leave to the reader. So I've got a few minutes left. This is sort of, we've got lists, we've built them up, that's all fine and dandy. But I want to show you a couple really neat things about this. This is kind of ugly, and we kind of hinted at these little things. These are called combinators. So we have what's called I, the identity combinator, or in the terms, all of the combinators have bird names, of course. So this is called the idiot bird, and this is called the kestrel. And so these are the core of Lambda, part of the core of Lambda calculus are these ideas of combinators where you can put them together to create other things. So the true is actually the kestrel. The false is what happens when I give the idiot bird to the kestrel. Now, there's a bunch of other combinators, and I want to show you one here. So notice that this is something that I'm actually executing two things. Let's find one that's a little bit more clear here. How about this? So this is, you give a refute a boolean. It calls not on that boolean, and then the results of that gets passed to assert. This is really executing sort of both of these functions. So it would be neat if I had another function called both that took two functions. we'll say func1, func2, and then the parameter. And it called func1, passing in what happens when you call func2. This is functional, basically composing these two functions. Now, oh, I need a hooray for bracket matching. So there's my t's. So using both, and of course both is a little bit too long to write, so we're just going to call it b. In this case, I could make refute. Well, what's the, I want to call assert. I want to call not, and then assert. And this should return me a function that takes a parameter and then composes those functions over it. And it does. So now I can build refute in terms of this combinator. This actually takes a function, takes another function, returns you a function that calls them like this. And you can use B all over the place. B is another combinator. It is called the bluebird. And so anywhere you have these, you can do this. So tail is actually B of second, second. Head is B of first, second. We can get rid of these. This is kind of craziness. I don't even know what that is. I'm not even going to try. So you can start using these and building these up as you go. Finding different combinators. What happens if you have a function that takes two functions and composes them the wrong way around? And start building up all these combinators. And all of these sort of basic combinators can be constructed and composed in this way. Either to build up true and false, Booleans end up being able to be built that way too, as you move along. So I'm kind of out of time, but if you would like to know more, there is a wonderful book called To Mock a Mockingbird, which is the sort of the first book that kind of gave the bird names to them. There's also a guy named Reg Braithwaite who wrote a book on, it's like kestrels and other silly birds or something like that. So if you look up his name, which goes into building a lot of the combinators and builds up computation from here. And then last but not least, Tom Stewart wrote a book on on computation or something like that. Fantastic book to read if you want more interesting craziness about this sort of thing. Yeah, so I like to end with a little bit of fun. There's pistachio. So there's where we get a clap. Awesome. Oh, he is coming. Good.
So we have a few minutes here. Why don't we wait? Are you done? Am I interrupting something?
No. I was leaving.
That clock says we have 2 minutes. So do we have mics for the audience? Can we roam?
As long as we have 2 minutes. Oh.
Is it on a rotating?
No, that's just I'm a manual rotator. You can ask questions if you want. Squeaks just turned 1.
Is it on?
Pistachio is about 9.5. We got them from the Anti-Cruelty Society. Are there actual questions? Yes.
Why combinator? Which one is that?
So yeah, we have to get into a pattern here. So wait for the mic, and then yeah, We got it, and then...
Oh, hello? Yeah.
There we go.
You hear about Y Combinator?
Yep.
And I'm wondering if it's actually real or imagined. And if it is real, could you please demo it?
I'm out of time. So the answer of real or imagined depends on whether you're talking about the combinator or the accelerator. We'll assume you're talking about the combinator. It is real, and the Y Combinator is actually used to handle recursion. In the standard sort of original lambda calculus, and in lambda calculus actually, you don't have names. You can't, like we assigned it add to list as this function, things like that. You don't get to give the name. And if you can't name it, then you can't like do a recursion and call yourself. And so what the Y Combinator does is it allows you, through this really crazy set of lambdas, to effectively do recursion. And what it's looking for, the way it does is that it keeps calling itself and calling back into itself, looking for what's called a stable point. So it's looking for where subsequent things are the same. And that then says, I'm done. There's your exit point. If you are interested and want a demo of it, there is no better demo than Jim Weirich's talk. So how many people know who Jim Weirich is? And how many people are going to be introduced to the greatest man ever? So Jim Weirich, amazing person, amazing programmer, sadly died recently, but just an amazing programmer. How many people ever went through the Ruby koans? Anybody? He invented those. He created those and all of that, or any of the language koans. He did a talk, a live coding talk at a couple different conferences where he basically derives the Y Combinator. And you are not going to get a better introduction to it than that. So I would highly recommend Jim's talk. I'm actually over time answering that. So how about another hand for Pistachio?
So my original vision for the stage was to have a couch, like a comfy setup. But I'm like, yeah, but no one's going to use it, so it's going to be weird. People are going to be wondering why is that super comfortable setup back there. And so Corey came to me one day and he's like, you know what I could use is a really comfy chair. So this is the Corey chair.
It is a very comfortable chair.
Please give
Awesome.
Corey a
Thank you.
round of applause. Thank you.